Breaking news. At 0241 UTC this morning, observatories on 3 continents recorded something no one was prepared to explain. Within a span of 0.8 seconds, a region of space long believed to be gravitationally silent erupted with energy across multiple wavelengths. Gamma-ray detectors in orbit spiked. Radio arrays on the ground went momentarily blind. Gravitational wave monitors registered a tremor that did not match any known cosmic event. Today, the impossible just happened. A black hole, an object defined by its inability to release anything, appears to have released everything. Moments ago, confirmation arrived from independent instruments, and the implications are staggering. This changes everything we thought we knew about gravity, time, and the fate of the universe itself. If you want real-time updates on unfolding cosmic mysteries like this, hit like, subscribe, and stay with us. What we are about to tell you is only the beginning. Within minutes of the first alert, automated systems at NASA's Goddard Space Flight Center flagged the event as a probable false positive. Black holes do not explode. They merge, evaporate over unimaginable timescales, or remain silent. Yet, as data continued to stream in from ESA's monitoring network and university observatories, that assumption collapsed. The signal was real, the source was consistent, and the location, 94 million light-years away in a quiet elliptical galaxy cataloged and studied for decades, left no room for easy explanations. By 0312 UTC, teams at Harvard, Caltech, and the European Southern Observatory were on emergency calls. The James Webb Space Telescope was retasked mid-orbit. Hubble's ultraviolet instruments were redirected. On the ground, the Atacama Large Millimeter Array in Chile locked on to the coordinates, while radio dishes in South Africa and Western Australia synchronized their clocks to the nanosecond. This was not one instrument malfunctioning. This was the planet watching the same impossible thing at the same time. To understand why this moment matters, we have to start with what black holes are supposed to be. According to every tested model of general relativity, a black hole is a one-way boundary in spacetime. Matter goes in, information goes in, energy goes in. Nothing, no light, no particle, no signal comes back out once it crosses the event horizon. For decades, this idea has survived every observation, every simulation, every experiment. Until now. 48 hours before the event, nothing appeared unusual. Archival data shows the black hole, designated BHX-1A, was behaving exactly as predicted. Its mass was estimated at 14 million times that of our Sun. Its accretion disk glowed steadily at temperatures around 12 million Kelvin. X-ray emissions were stable, no jets, no flares, no warning. 11 hours before the event, however, something subtle changed. Gravitational wave detectors in Italy registered a faint, rhythmic oscillation, far below alert thresholds, but later analysis would show it followed a repeating pattern every 3.2 seconds. 6 hours later, spectroscopic data from a Chilean observatory showed a shift in the iron K-alpha emission line. Not a red shift or blue shift consistent with motion, but a symmetrical broadening, as if space-time itself around the black hole was vibrating. No known natural process could produce such precision. At 0240 UTC, 1 minute before the explosion, radio telescopes detected a brief silence. Not noise, not interference, a sudden drop to baseline cosmic background levels, lasting exactly 0.6 seconds. Then, at 0241 UTC, everything happened at once. Gamma-ray detectors aboard NASA's Fermi observation saturated. Energy output was calculated at 10 to the 46th joules, equivalent to converting the mass of Jupiter entirely into energy in under a second. Infrared sensors saw a flash expanding outward at a significant fraction of the speed of light. Gravitational wave observatories registered a sharp asymmetric spike, unlike mergers, unlike supernovae, unlike anything in existing catalogs. And at the center of it all, the black hole's signature vanished. For 1.3 seconds, BHX-1A was simply gone from every instrument. The first theory to emerge was catastrophic accretion collapse. Dr. Alina Markov, a theoretical astrophysicist at Caltech, suggested the black hole may have consumed an unusually dense object, perhaps a neutron star, triggering a runaway instability. Simulations were run within hours. They failed. The energy output was too clean, too symmetrical, and most importantly, there was no debris, no fallback material, nothing left behind that such a violent interaction should have produced. Another hypothesis involved Hawking radiation, but on steroids. In theory, black holes can evaporate over timescales longer than the age of the universe, releasing energy slowly. What we observed was the opposite, a rapid, coherent release of mass energy, as if the black hole had been holding something back, waiting. By 05 UTC, a second wave of anomalies complicated the picture further. Radio telescopes detected repeating pulses from the same region, not random bursts, but evenly spaced emissions at intervals of 2, 3, 5, 7, and 11 seconds, prime numbers. This was no longer random, it was structured. Spectral analysis showed the pulses spanned from 1.4 GHz radio waves up to soft X-rays with precise harmonic relationships. Dr. Samuel Reyes at the European Space Network described it bluntly in an internal memo: "Astrophysical sources do not count." As debates intensified, a classified report leaked from a joint NASA-ESA task force. According to preliminary gravitational modeling, the space-time curvature at the explosion site inverted for a fraction of a second. Instead of pulling inward, it pushed outward. General relativity allows no such solution under normal conditions. Meanwhile, Earth felt subtle echoes of the event. At 0617 UTC, 3 communication satellites experienced brief synchronization errors. GPS timing drifted by nanoseconds, small but measurable. Magnetometers in Scandinavia recorded a 0.4 nanotesla fluctuation with no solar activity to explain it. Even migratory bird tracking data later showed minor deviations in flight paths during the same window. Nothing dramatic, nothing apocalyptic, just enough to suggest a connection. Inside control rooms, the mood shifted from excitement to unease. Screens replayed the data on loop. Engineers whispered. Scientists argued. I remember staring at the waveform, realizing that if this interpretation was correct, then black holes were not dead ends of physics we believed them to be. 2 camps quickly formed. The first argued for an exotic but natural explanation, a phase transition in space-time itself, perhaps involving quantum gravity effects near the singularity. According to this view, the black hole did not explode, it transformed, releasing stored energy as it shifted into an unknown but natural state. The second camp was quieter, more cautious, and far more unsettling. They pointed to the precision, the timing, the mathematical structure. They asked an unspoken question: what if this was not a failure of physics, but an application of it? Escalation came 19 hours after the initial event. A fragment, yes, a fragment, appeared in infrared data, a compact mass roughly equivalent to 0.8 solar masses moving away from the explosion site at 12,000 kilometers per second. No accretion disk, no tail, just a dense object on a controlled trajectory. Then, without warning, it vanished from all sensors simultaneously. Silence returned, but it was not empty silence, it was expectant. Governments were briefed, agencies stopped commenting, public statements emphasized caution, calibration errors, and the need for peer review. Privately, emergency committees were formed, new observation protocols were drafted. The James Webb Telescope remained locked on the coordinates, waiting. And then 36 hours later, a final signal arrived, a low-frequency gravitational ripple repeating every 88 seconds, gradually fading, the last measurable imprint of something that should never have happened. Now, in the quiet aftermath, we are left to reflect. For a century, black holes have represented the ultimate limits of knowledge, the places where equations break down, where information is lost. But maybe that was never the full story. Maybe they are not tombs, but vaults, or gates, or something we are only beginning to understand. Perhaps we are not witnessing the end of certainty, but the beginning of a deeper question. If black holes can release what they consume, if they can change state, or even respond to conditions around them, then the universe is far more dynamic and far less predictable than we imagined. As of this moment, the source remains quiet, but the data remains, and scientists around the world are still watching, because the most unsettling possibility is not that the black hole exploded, but that it chose to. Subscribe to follow the next update. This story isn't over, and the universe may have just shown us that it's capable of far more than we ever dared to believe.